Mark your own. And circuit. So it says, the following diagrams show a charged particle carrying, or a current carrying wire in a magnetic field. For the diagram, use the right-hand rule. You can show your directions by drawing an X to show into the page or a dot to show out of the page. Let me zoom in on each one of these. And if you're struggling with this, I strongly, strongly encourage you to follow along with me. Number one is a trick question. Is the electron crossing magnetic field lines? There is going to be no force in number one, whether it was an electron or a proton. You have to cut across. That's why the QVB equation had right angles as subscripts in it. Number two, Zach, which way is the positive charge moving? So everybody point your thumb upwards. But stop doing this. You should have your hand like this right away, okay? This, when you're curling your fingers, that's for the solenoid or the single wire, not for a moving charge. Zach, what direction is the magnetic field? Pointing to your right. So everybody, your thumb should point up, your fingers point right. What direction is the force then? Into the page. So you could write into the page, or because I'm lazy, I'm going to use the abbrev. Remember, that's meant to be the tail feathers of an arrow retreating away from us. So that's how you can remember it. 1 mark. Number 3. Now we have a current carrying wire. Mason, what direction is the current? What direction are the positive charges moving if they could? Same answer. Yeah, this is one of the many reasons we defined current as which way the positives would like to move. So I'm going to point my right thumb to the right. Magnetic field is which way? So magnetic field, which way is the force? And so you could say out of the page, or if you're particularly lazy, you can draw a circle with a dot. That's the point of an arrow coming out of the page right between your eyes. Number 4. It looks like the velocity of this electron is into the page. Do I deal with electrons? So an electron into the page is the same as a proton, what? So I'm going to point, for me, I would point my thumb at me. Magnetic field to the left. Which way will this electron feel a force? And so you could either write an arrow down, or you could write down the page. Good. Now we have a proton traveling to the right and a magnetic field out of the page towards us. So proton traveling right, magnetic field out of the page towards us. Honestly, facing the board, the only way I can do that is to kind of tuck my hand like this, but I can. Down the page, is that correct? So you could either write an arrow like that, or you could say down the page. Okay, I guess I'll point my thumb up and right diagonally. Magnetic field into the page. You know what? The force is that way. Up and left. Out of paper. Okay, so the current is coming out of the page towards us. So I'll point my right thumb out of the page towards me. Magnetic field to the right. I got to bend a little. No, I'll just take my hand out. And it looks like the force is up the page. Looks like the electron is traveling up and left. I don't deal with electrons. So an electron going up and left is the same as a proton going down and right. Magnetic field is coming out of the page towards me. A little bit awkward, but you know what? I think this electron will feel a force down and left, not up and left. Is that okay, Owen? Okay. Then we turn so 1 mark for each of those. I guess that page is out of 8. Then we turn the page. Oh, now we have the solenoid rule. So the solenoid rule, I have to imagine that I'm holding the solenoid in my hand here. I'm going to zoom in again. I'm going to label the current. Looks like the current goes this way, this way. So I hold the solenoid in my hand. I curl my fingers in the direction of the current. And Danica, you are correct. Your thumb, technically what you're being told is the direction of the magnetic field inside the solenoid. This is north. This is south. Inside here, it goes that way, and outside here, it goes that way. So that's north, that's south. I know it looks like inside the solenoid, the magnetic field is pointing from south to north. It's not. It's because magnetic field lines have no beginning and no ending, and our rule tells us the magnetic field outside the solenoid. It looks like in this diagram, I got the current going that way. So I would hold my hand like this. That's north, that's south, 1 mark. And in this diagram, I'm going to have to figure out the current. I can do that. Goes like that, like that. Okay, so it's coming this way. So that's north, that's south. What if they ask me to calculate how big the magnetic field is? Remember, the magnetic field is mu naught N times I over L. That'll be on today's take-home quiz, but that would be a good combination kind of a question. All right. Determine the direction of the force on the wire for each of the following 3 cases. Again, let me zoom in on this first one. The problem here, so I guess the wire, the current is coming out of the page towards me, but they didn't tell me the direction of the magnetic field. Or did they? What direction do magnetic field lines always point from what to what? So I would draw that in. I would say there's the B field, there's the B field, and now I can do my right-hand rule. Coming out of the page towards me, I got to stick my hand way out here so that I don't dislocate my shoulder, but it looks like up the page. Yes? 1 mark. Here, it looks like the current is going into the page, and the magnetic field lines are pointing to the right. That's going to feel a force down the page. For number 3, or for the third one, I think I'm going to have to figure out what the magnetic field from the solenoid is, direction-wise, and then I can figure out what force the wire is feeling. So the first thing that I did is I drew in the current. I said, okay, I'm going to hold this solenoid like this. No, I can't. That doesn't work. I have to hold it like this. So it looks like this end is north, this end is south. And so the magnetic field line would point from north to south. Right there, I think the magnetic field line is pointing downwards, right where the wire is. So now I've got my hook. Wire's coming out of the page. Magnetic field line is pointing downwards. You know what? I'd probably just tuck like that is how I would do it. It looks like that wire is going to feel a force to the right. Yes? To the right. And again, I apologize for people who are watching or trying to figure this out on YouTube because you can't see what I'm doing and I haven't figured out a way to make it any clearer. This is a lousy unit to try and learn from YouTube. So 3 marks for that. Sketch the path. Okay, it's a proton. So proton is moving to the right. I guess those dots are the magnetic field lines. They're coming out of the page towards me. So I think this proton would feel something like that. It would be a curved path, circular path, as opposed to a magnetic field into the page. Which way am I going? Boom, boom. Yeah, that would feel I'd be looking for a path like that. But these would curve in a circle, and you would be able to say magnetic force is what's pushing me in a circle. QVB equals either mv squared over r or m4 pi squared r over t squared. By the way, this is not only used in particle accelerometers, this is also used in mass spectrometers. They're fancy gadgets that can take an ionized charge and based on the radius of that charge, calculate its mass. You get the M by itself in QVB equals MV squared over R. There's all sorts of neat applications for this. Can you give yourself a lovely score, please, out of 16? Number 1 on the take-home quiz. First of all, does yours say take-home quiz 2? I think yours is fixed because I'd added an extra quiz, but the one that I originally photocopied, we need to change it from number 1 to number 2. So number 1, a conducting wire is carrying current upwards. There's a mysterious magnetic field. I didn't draw it on the page, but the wire is feeling a force directed out of the page. What's the correct direction of the magnetic field? And my point is, on your test, as far as I'm concerned, for this weird right-hand motor rule where you're going thumb, fingers, palm, I only need to give you 2 of the directions, and you can figure out the third one. So I can ask you to find the direction of the force or the field or the moving charge or current. Okay? Number 2 says, suppose the magnetic field is changed, and now the wire in question 1 experiences a force pushing it to the left. What's the direction of the magnetic field? Number 3, a stream of protons is acted upon by a magnetic force of that while traveling perpendicular to a magnetic field of that. What speed are the protons traveling at? I think you're going to use QVB. A wire carrying 5.2 amps as shown in the above diagram. The wire experiences a force of 2.4 times 10 to the negative 2 newtons. What's the strength of the magnetic field? What's the direction of the magnetic force? Turn the page over. Number 5, an electron, it's an electron, traveling at 6.2 times 10 to the 6 meters per second, moves perpendicular to a magnetic field of strength 8.5 times 10 to the negative 3 teslas. What's the magnitude of the force? And then it's pushed into a circle. What's the radius of the circle? Oh, and just for giggles, part C, what's the kinetic energy of the electron? Just doing a bit of review. Number 6, what's the magnetic field strength inside a solenoid of length 3.2 centimeters, having 600 turns of wire with a current of 4.5 amps? And then number 7, a bar magnet is free to rotate while in a magnetic field. Initially, it's positioned as shown. Which diagram shows the final orientation of the bar magnet? I'll let you think about that. So this is due tomorrow, next class. But we're not pressing pause. I got too much cool stuff to show you. I'm going to teach for about 15 or 20 minutes, and then I'm going to press pause. But I do want to hint a little bit at how it is that we generate power. Also because this is really good right-hand rule review.
Wait, this is probably the best. We're not going to be allowed to have like our right-hand rule sheet.
No, you need to know it to memory. But I'm going to be doing so many, I hope you have. Like, I'm going to be doing a bunch in this lesson too. And I think I forgot to press pause on my YouTube videos, so sorry for those of you at home on YouTube. Going, what the heck's going on? I'm handing stuff out. Normally I remember to press pause, but I think I forgot. Did I press pause? Didn't. Silly. This is the unit I would have got to after this. I want to do an introduction, A, because it's nerdily cool, but B, it also has a whole bunch of right-hand rule applications, so it's good practice. In the previous unit, the one we just finished, we learned that when electric charges move, they produce a magnetic field. When current is running through a wire, you curl your fingers in the direction of the magnetic field. Or when a solenoid, a bunch of wires wrapped together, generates a magnetic field, moving charges create a magnetic field. In addition, a magnetic field will exert a force on moving charges. Early in the 19th century, scientists such as Michael Faraday of England and Joseph Henry in the U.S., they knew this and they asked the obvious question, look, if a current can produce magnetism, can magnetism produce current? Can we use magnets to generate electricity? Little recall, Electromotive Force Emf, or that little E symbol, it's an archaic word that refers not to a force, but to the voltage of a cell. So I'm going to be using capital V and that curly E interchangeably. So here's our first thought puzzle. If a piece of wire is physically just pulled, say on a rope or in your hand, through a magnetic field, the charges in the wire will experience a magnetic force. Because the electrons in a metal are free to move around, but the positive nuclei are not, the negative charges will move to one end of the wire. We're also going to pretend the positive charges move to the other end, because negatives moving in one direction is the same as positives moving in another direction. So example 1 says this: which end of this wire will be negatively charged due to the magnetic force on the electrons? I'm going to zoom in a little bit. And what I'd like all of you to do, this is a metal bar right here. Draw one proton sitting in the middle right there. That's an atom. Sarah, what's the velocity? What direction is the velocity of this bar based on the arrow that you see here? Down, okay? So which way is this proton locked inside of the bar also traveling? Same answer. Down the page. All of you point your right thumbs down the page, please. What direction is the magnetic field? It says into the page. What direction will these protons feel a force? To the left or to the right? So this side of the bar will become positively charged, and also the electrons will feel a force. They're going to become negatively charged. And what you've really done, Danica, is you have done work separating charges. The same thing that a battery does through a chemical reaction, you've actually done through motion. And you've exerted a force on those charges called QVB. Because forces come in pairs, you would actually feel a force tugging against you as you moved that bar through this magnetic field. You would actually feel it pulling up against you. The direction of the force it's going to get more complicated, but that's a great question. The charges feel a force moving them to the left and to the right, but if you're actually asking what's the overall magnetic force on the bar, different question. We'll get to that. But you can already see, what if we clamped wires on the end of this? Wouldn't current flow? Because I'd have positives moving in one direction. And the answer is, yeah, I can now create current from motion. If I just complete the circuit, put a resistor down here, and it'll light up and it'll power. And you might say, no, unless you do it. Yeah, we do this all the time. Since charges have been separated, which takes work, we have voltage, since voltage is defined as potential energy per charge. This is sort of like lifting up a mass. You stored potential energy, except here we've separated charges. But remember I told you voltage was kind of like height. We call this voltage induced by motion. Sorry, we call this voltage induced by motion, motion voltage, because the energy in this does not come from chemistry like in a Duracell battery, but from motion. In other words, motion can induce an EMF. Motion can induce a voltage. How much? Well, V equals potential energy per coulomb, right? And potential energy or work per coulomb is force times distance per coulomb. What force? Magnetic force. Oh, that's fair game for your test coming up. What was the magnetic force on a single moving charge, like a proton, on your formula sheet? What was the equation? Don't turn the page. I think we're still on this page, Zach. The page with all the equations on it, so not your data sheet. And we're in the magnetic forces section, which is probably right after circuitry. So you're going to be seeing this on Thursday, and it's on your take-home quiz. What's the magnetic force on a moving charge? So you're going to find F equals. What's the symbol for a charge? So you're probably looking for an equation that has an F and a Q in it. What's the symbol for magnetic field? You're probably looking for a force equation. What? Okay. Q, V, B. Oh, you know what? It turns out the Q's cancel. The voltage induced by motion is equal to, usually we write it as B, V, and then instead of D, we use an L. Is that what it is on your formula sheet? So you should see, in fact, it might not even be a V, it might be an EMF symbol. Is it BVL or VBL? And they have to be all perpendicular to each other, just as before. BLV, is that what I wrote it as? I couldn't remember the order. BLV. The faster you move that bar, that piece of metal through the voltage, through the magnetic field, the more voltage. The stronger you make the magnetic field, the more voltage, or the longer the bar. Usually, we're not going to muck around with the bar length. We'll muck around with the speed of the magnetic field. Okay? And it's perpendicular. We only get voltage when they're all at right angles to each other. What if they're not at right angles to each other? Example 3. Turn the page. So again, here's our bar, but instead of the bar being horizontal, it's which was perpendicular to the velocity, the bar is aligned in the same direction as the velocity. Let's do the same thing. Let's put a positive proton right there in the middle. Garrett, which way is that proton moving? Look at the velocity vector. Which way is that proton moving? Yeah. So everybody point your thumbs down the page. What direction is the magnetic field? Which way will the proton feel a force? To the right. But here's the problem. Look at that. Is there really anywhere for it to go to the right if the bar is oriented in this direction? Barely any distance at all. Yeah, it'll move over a couple of centimeters maybe, and the electrons will move over a couple of centimeters in the opposite direction. You will technically separate the charges a little bit, but nowhere near what you're going to get in this situation here, where you can really separate the charges. Zach, you figured it out okay?
Oh, you made it into the page.
Yeah, you have to read the directions. Yeah.
Right.
Okay. Okay. So here, how much voltage? It says indicate which end of the wire is negatively charged. Technically, that'll be negative and that'll be positive, but very little separation of charges. So very little work, so very little voltage. So here's a nice example. It says, find the voltage induced by motion across the ends of the moving wire and indicate polarity. I did a quick look. Are all three of these at right angles with each other? The bar is like this. The magnetic is horizontal. The magnetic field is vertical. It looks like the velocity is into the page. They are. So there is going to be an induced voltage. This here, by the way, BLV, not going to be on your test on Thursday, so don't panic on that. But let's quickly crunch it. It looks like the magnetic field. The terminology here is all fair game for your test in terms of magnetic field and speeds. It looks like the length is 0.8. It looks like the speed is 5.25. And I get do I get 5.25 volts? Is that right? Which end of the bar will be positive? Which end of the bar will be negative? Let's see. So again, I always draw a little token proton in the middle of the bar. What direction is the bar, and therefore the proton, moving? It looks like V is into the page. So everybody point your thumbs into your page or into my board. What direction is the magnetic field? Yeah. Which way will the positives, which end of this bar will be positive, the left side or the right side? Which side? Left side? So this will be the positive side, and this will be the negative side. It turns out you can capture voltage from an airplane that's moving through Earth's magnetic field. And they do this on jets. Okay? The plane is moving at 320 meters per second to the right. They gave me two lengths. They gave me the length of the fuselage and the wingspan. Which of those two lengths is perpendicular to the velocity? The 60 or the 150? The 60 or the 150? The 60. Okay, so the voltage is going to be BLV. The B is Earth's magnetic field, which is higher at altitude than on the Earth's surface. So up there, 0.008 Teslas. The length is 60. The speed is 320. How many volts can we generate between the wings? Garrett, what'd you get? What? How much?
152.6.
That's enough to run stuff, and they do. I don't know what they do with it on modern airplanes. On old airplanes, back when everything was smoking, you had a little push-in cigarette lighter at every single seat that you would push in, and it would slowly heat up and then pop out. They were running those from this voltage, I believe. Why not? You're going through a magnetic field with a big piece of metal. Use it. Now, that's not free energy. That energy, because remember, voltage is energy per coulomb, that's coming technically from their fuel. They're getting slightly worse gas mileage because of it, but still. Yeah. No, and the cigarette lighters didn't work that way. You would push them in, and they would slowly heat up and then pop when they reached a certain temperature. They were trickle chargers, I suspect. I really wanted to do that because it was good practice of the right-hand rules. I think you'll agree. And it's kind of cool. Now we'll ask, what if you connect it to a conducting wire? We'll do that tomorrow. Oh, and then we'll ask, what if you supply a current? And I'll show you how you can make a railgun. Because this is the technology behind railguns. And a possible way to launch spacecraft from the International Space Station or larger space stations someday. There's some neat applications here.